Okay, in this lesson we're going to be looking at Unit 6, Chapter 6, Trigonometric Identities. We're going to be solving trigonometric equations using identities. This is Part 2. And we're going to be solving simple trigonometric equations within a specified domain. Okay, first of all, as I said, this is from Section 6.4, and the focus is going to be on, I'm just trying my pointer here, solving trigonometric equations algebraically using known identities and determining exact solutions of trigonometric equations where possible. Okay, here we go. Again, your double angle identities, you need to know these, of course, your difference identities, your sum identities, and your Pythagorean identities. Again, all of these will be given to you on your exam, so there's no need of memorizing them, but you need to be able to apply them. Okay, let's have a look at some examples. The best way to deal with this is to simply do some examples that involve solving trigonometric equations. So the first thing we're going to do is solve by substituting trigonometric identities. So here's an example. We're asked to solve this equation, sine 2x, subtract cosine x equals 0, algebraically over the domain 0 is less than or equal to x, which is less than 2 pi. Okay, so sine 2x minus cosine x. The first thing we're going to do is we're going to replace our sine 2x, of course, with 2 sine x cosine x. Subtract cosine x equals 0. Now if you look at this equation here, we have both sines and cosines in the equation. However, if we remove a common factor of cosine x, we will create a nice little equation here which looks like 2 sine x, subtract 1, the subtract 1 must go there, equals 0. Now, we still have two trigonometric functions here, both sine and cosine, but we can apply the zero product property because we got two things multiplied together that equal 0. So the zero product property simply says that the first thing equals 0, or the second thing must equal 0. If we take the second equation and solve for x, sine x equals 1, 2 sine x equals 1, so sine x will equal 1 over 2. And you see I've created two equations here. I've created cosine x equals 0, and I've created sine x equals a half. I need to solve both of those equations within that specific domain. So let's solve both of these. Cosine x equals 0. So where is cosine x equal to 0? In the domain between 0 and 2 pi. Well, we can do this a couple of ways. We can do a sketch of the graph of cosine x between 0 and 2 pi if you wish. Or we can think about the unit circle as well. That will help us determine as well the locations where cosine x is equal to 0. If I were to just sketch the unit circle here, we've got a point at x is 1, y is 0 here. X is 0, y is 1. We've got negative 1, 0, and of course 0, negative 1. So we're looking at where's cosine x equal to 0 between 0 and 2 pi. Now notice your domain again does not include 2 pi. It's between 0 and 2 pi, including 0 but not including 2 pi. So you can see that cosine x is equal to 0 here and here. So if we were to write these two solutions, we would get an answer of x equals pi over 2 as one solution, and as well 3 pi over 2. Which of course is the same as 90 degrees and 270 degrees. That is where cosine x equals 0. Now what about where sine x equals a half? Well, if we again think about our unit circle for sine x equals a half here, let's construct another unit circle. Now, sine x equals a half. Sine is positive in two places. You must consider the fact that sine is positive in two places. That means we'll have a terminal arm in each of these two quadrants, because sine is positive in quadrants 1 and quadrants 2. Sine is the second coordinate of our point on the unit circle here. So we're looking for a point that has a sine of a half. Well, you know that if the sine is a half, the cosine is root 3 over 2. And you should recognize that point as having a reference angle of 30 degrees or pi over 6. So we got a reference angle of pi over 6. We'd have a reference angle of pi over 6 on this side as well. So our two values of x being measured from the positive x-axis, of course, would be x is equal to pi over 6 is one answer, And the other answer would be, of course, 5 pi over 6, because we're 1 pi over 6 less than 6 pi over 6. This is 6 pi over 6 right here, which is pi, and we're 1 pi over 6 less than that. So you see I have 4 solutions within the domain between 0 and 2 pi. Okay, there's our first example. Let's have a look at another example. This one involves factoring. Solve the equation 2 cosine x plus 1 subtract sine squared x equals 3. Algebraically over the domain again, same domain between 0 and 2 pi. I can rewrite this equation as 2 cosine x plus 1 subtract sine squared x subtract 3 equals 0, which gives me 2 cosine x minus sine squared x subtract 2 equals 0. Now we have a scenario here again where we got 2 trig functions, both sine and cosine in the same equation. If we could remove a common factor, like we did in the previous example, then we wouldn't have to worry about that. But in this case, we can't. So we actually got to replace sine squared x with something, or cosine x with something. But obviously, I think the most obvious thing to do here is to replace sine squared with 1 minus cosine squared. And when I do that, I've at least created an equation now with 1 trig function, which is cosine. Let's see what I get when I do that. I get 2 cosine x, subtract 1, plus cosine squared x, subtract 2 equals 0. Now if we simplify, I get cosine squared x, I get a plus 2 cosine x, subtract 3 equals 0. You should now recognize this as a quadratic equation that is factorable, hopefully factorable. So let's factor it and see. Cosine x, 3 and a 1 will go here. I want a positive 2, so I had to make my 3 positive and my 1 negative. Now I always double check, whenever I factor, I always double check by multiplying both of these together and make sure I get what I started with. So cosine x times cosine x is cosine squared. I got cosine times a negative 1 is a negative 1 cosine. And I got a 3 cosine when I multiply these two together. So a negative 1 cosine and 3 cosine is a positive 2 cosine x. Plus 3 times a negative 1 is a negative 3. So I got a factor right. And you should always check your factors. There's no reason to get your factoring wrong, because you can always check and see if you got it right. If you got it wrong, go back and fix it. Okay, what I've done now is I've created, again, an equation where 2 things are multiplied together to equal 0. So using our zero product property again, I got cosine x plus 3 is equal to 0. And I got cosine x subtract 1 is equal to 0. If I solve the first equation for cosine x, I get cosine x equals negative 3. Solve the next equation for cosine x, I get cosine x equals 1. Now, cosine x equals negative 3. So again, I got 2 equations to solve here. We want to recognize that. Cosine x equals negative 3 and cosine x equals 1. You should recognize the first one as being undefined. This one is undefined. And it's undefined because cosine x cannot have a value greater than 1 or less than negative 1. And we know that if you think about the graph of cosine x. If you think about the graph of cosine x, the graph of cosine x looks like this, doesn't it? The maximum value on the graph is 1. The minimum value on the graph is negative 1. Cosine x cannot equal negative 3. So that's why we say cosine x is undefined. Now, where is cosine x equal to 1? Well, since I have the graph of cosine x here, I guess we can plot our points. This, of course, is 2 pi here, and this is pi over 2. This will be pi, and here will be 3 pi over 2. Now, so where is cosine x equal to 1 from the graph? Well, from the graph we can see, and I'll highlight the points, cosine x is equal to 1 here and here. So it seems that the answer is 0 and 2 pi. However, if you look at your domain specifies that our value of x has to be between 0 and 2 pi, including 0, but not including 2 pi. So the only solution to this equation is x is equal to 0. x is equal to 0. Because 2 pi is outside of our domain. I'll just make a note of that here. Oops, let me fix that. 2 pi is outside the domain. So because of that, 2 pi is not a solution. Okay, example 3. Solve the equation cosine squared x equals cotan x times sine x algebraically in the domain between 0 and 360. Let's do that. Cosine squared equals cotangent, which is cosine over sine, times sine, which is simply going to give me cosine squared x equals cosine x, because of course, I'm sure you'll agree the sine x's will cancel here, right? That sine x will cancel with that one. Now, if I bring the cosine x over to the left side, get it equal to 0. Now, you should see here that I can factor this by removing a common factor of cosine x again. And again, use the zero product property like you saw me use the last two examples. We do the same thing again. And I get cosine x is equal to 1 and cosine x equals 0. Cosine x equals 0 and cosine x equals 1. And again, if you look at your domain this time, the domain is between 0 and 360, not including 360. So we're looking for answers in radians between 0 and 360. So let's solve both equations. And I guess one of the quickest way to do that would be to use our unit circle. We could use the graph of cosine like you saw me use the last example. It doesn't matter. If we think about our unit circle, we got the points 1, 0, 0, 1, negative 1, 0, and 0, negative 1. Cosine is the first coordinate, so where is cosine x equal to 0? Cosine x is equal to 0 at, again, 90 and 270. So I'm going to write, as part of this solution over here, x is equal to 90 and x is equal to 270. Where's cosine x equal to 1? Cosine x is equal to 1 right there at 0 and 360. But remember, 360 can't be part of our solution. So the only solution there would be 0 degrees, where cosine x equals 1. And at this point, you probably think you're done with this equation. And you're done, and we got our solution, 90, 0, and 270. The reality is we're not done. The reason being is because we need to consider any non-permissible values. And there are non-permissible values in this equation. Because if you look at the equation when I replace cotan with cosine over sine, I got a denominator here of sine x, meaning cotan x is undefined when sine x equals 0. So sine x cannot equal 0. So where is sine x equal to 0? Well, if you look at your unit circle again, sine x is equal to 0, right? And I'll use a different color to highlight it. Sine x is equal to 0 at, let's see, 90 and 270. Sine x is equal to 0 at 90 and 270. So, x cannot equal 90 and x cannot equal 270. Because again, if x were equal to 90 or 270, this would be undefined. Oh, I'm sorry, I've made a mistake here, haven't I? I've done where cosine x is equal to 0, not sine x. I need to go back and correct that. Sorry, guys. Apologize for that. Where is sine x equal to 0? Sine x is equal to 0 at, let's get this correct. See if I can move this around here. Sine x is equal to 0 at 0 and at 180. There we go. That's better. At 0 and 180. So, in other words, between 0 and 360, x cannot equal 0 and 180. So if x can't be 0 or 180, because if 0 and 180 were used here, the sine of 0 is undefined. Sine of 0 is 0, and therefore cosine divided by 0 is undefined. So we cannot have a value of 0 or 180. Now we've already said, if you look at your three answers, that x could be 90, 270, or 0. X can't be 0. This is a non-permissible value. our only solution to this equation are, the solutions are 90 degrees and 270 degrees. So you need to be very careful with these equations, that you also need to consider any non-permissible values that occur. So you look at your answers and you need to determine, are these non-permissible? Are any of these non-permissible? If there are, you have to cross them out and say it's not a solution. Very important point there. Here's an example here. Solve. Tan x times cosine x equals 1 between 0 and 2 pi. This little squiggly line shouldn't be there, so let's get rid of that for a minute. So our possible solutions are 0 and 90, 180, and no solution. Why don't you pause the recording at this point and try this question on your own before I actually do it. Okay, let's have a look at it. I got tan times cosine equals 1. Tan is sine over cosine times cosine. Cosines cancel, and I'm left with sine x equals 1. Okay, pretty simple. If we look at our unit circle, where is sine x equal to 1? And let's see if I can get it right this time. Last time I messed that up, didn't I? So let's see if I can get it right this time. Sine x equals 1. Okay, we got the point x is 1, y is 0 here. X is 0, y is 1. Negative 1, 0, and 0, negative 1. So where is sine x equal to 1? Sine x is equal to 1 at 90 degrees. So again, we're going to assume that the answer is x equals 90 degrees. However, just as in the last example, we got to check and see if x equals 90 is a permissible value. Are there any non-permissible values here? If you look at the ratio sine x over cosine x cannot equal 0. Cosine x cannot equal 0. So where is cosine x equal to 0? Cosine x is equal to 0, looking up at your diagram here, at 90 and at 270. So 90 and 270 are non-permissible values. Our solution was x equals 90, but we've just discovered now that that's non-permissible. So because that's a non-permissible value, the correct solution is no solution rather than 90. A number of students will give the answer of 90 degrees here rather than no solution because they're not considering the non-permissible values. I stress the point here, whenever you solve an equation such as this that involves trigonometric functions, whether it be tan, secant, cosine, whatever it is, okay, you must consider if there are any non-permissible values. And then you can see that in the last two examples that non-permissible values did exist, and we had to consider those. Okay, example 5, solve. Sine times cosine equals negative 1 over 2 between 0 and 2 pi. You may want to pause the recording again. Try this one on your own. If we look at this equation, we can see that we have a sine and a cosine on the left side, nothing on the right side, only negative 1/2, but there's no trig function there. And again, normally if we have two trig functions, it makes it difficult to deal with. However, if we were to multiply the entire equation through by 2, let's see what we would get. Multiply everything by 2. So I would have 2 sine x cosine x equals negative 1. I'm simply multiplying this side by 2 and I'm multiplying this side by 2, right? You should recognize now that 2 cosine x, though, is sine 2x. So now I've got sine 2x equals negative 1. At least I've got one trig function. In order to solve this equation, we actually got to go back and think about what we did in chapter 4. Because we did solve equations like this in chapter 4. And what we do is this. We let theta equal 2x. And we solve for theta. So if we let theta equal 2x, I'll get sine theta equals negative 1. So where is sine theta equal to negative 1? Well, I think you'll agree sine theta is equal to negative 1 right here at 3 pi over 2. So my solution for sine theta here equals negative 1. We're going to write the general solution first. That's how we solve these. Whenever we let theta equal something, we find our general solution. So we're going to write theta is equal to 3 pi over 2 plus 2 pi n, where n is the number of I. But remember, theta is equal to 2x. So I got to replace my theta with 2x again. So we get 2x equals 3 pi over 2 plus 2 pi n. Divide both sides by 2 and multiply by a half. I'm going to get 3 pi over 4 plus pi n, where n is the number of I. There's my general solution for x. I want specific solutions between 0 and 2 pi. So what I need to do now is I need to substitute in values of substitute in values of n into this equation here until I exhaust all the answers between 0 and 2 pi. So let's start with n equals 0. If I plug in n equals 0, let's do it in our head here. If I plug in n equals 0, I'll get x equals 3 pi over 4. Is 3 pi over 4 within the domain between 0 and 2 pi? The answer is yes, so that's a suitable answer. Let's plug in n equals 1. If I plug in n equals 1, I will get 3 pi over 4 plus pi, which is 4 pi over 4. So that will give me x equals 7 pi over 4. Is 7 pi over 4 in the domain between 0 and 2 pi? The answer is yes. Let's plug in n equals 2, because we need to plug in all the values of n until we exhaust all answers in both directions, in the positive direction and in the negative direction. So if I plug in n equals 2, I'll get x equals, and again, I'm doing this in my head here, but if I plug in n equals 2, I'll get 2 pi. Now 2 pi is 8 pi over 4. 8 pi over 4 plus 3 pi over 4 is 11 pi over 4. Is that within our domain between 0 and 2 pi? The answer is no. That's outside our domain, because that's greater than 2 pi. So let's go in the negative direction. Let's plug in n equals negative 1, and let's see what we get. If I plug in n equals negative 1 here, I'll have negative pi, or negative 4 pi over 4, plus 3 pi over 4 is a negative pi over 4. Is that in the domain between 0 and 2 pi? The answer is no. So as soon as we encounter an answer in the positive direction and in the negative direction that's outside the domain, we don't need to do anymore. The only two solutions that fall within this domain are 3 pi over 4 and 7 pi over 4. The correct answer is D. That was a little tricky because it involved the work that you did in a previous chapter. But again, you need to bring all this together at this point. Certainly for your public exam you do. Okay, let's have a look at one more example before we clue up. Secant squared x times cosine 2x equals a negative 2, again, between 0 and 2 pi. Again, we're always looking at every one of these examples that I'm doing in this lesson involves within a specific domain. The next lesson we'll do involves general solutions. Okay, secant squared x times cosine 2x equals a negative 2. I've looked at this question earlier, and there's a couple of ways we can do it. And I tried to decide, which would be the most suitable way of doing it so that you guys would follow it best. So maybe I'll look at least show you how we can do it two ways. Let's see. Secant squared x. Well, I think you'll agree that I need to rewrite that as 1 over cosine squared times cosine 2x. Now I'm going to replace my cosine 2x with one of three possibilities. And I don't know if it really matters which one we plug in here. I think we'll still work out to give us the same answer, regardless of what we use. I'm going to use cosine squared minus sine squared. I'm going to use that one. Cosine squared minus sine squared. When I do that, I'm going to get, if I multiply the 1 over cosine squared in through, I'm going to get cosine squared x over cosine squared x, subtract sine squared x over cosine squared x, equals a negative 2. Well, of course, that's 1. Subtract sine squared x over cosine squared x equals a negative 2. At this point, I got a couple of options open to me. I could replace sine squared over cosine squared with tan squared. So I could do this. I'll call this option 1, okay? Option 1. I can write this as 1 minus tan squared equals negative 2. And that will give me negative tan squared is equal to a negative 3. Therefore, tan squared x is equal to plus or minus the root of 3. And all we need to do now is solve that equation, tan x equals plus or minus root 3. Some of you may recognize that as being a special case, but it's a little more difficult to determine what the value of x is. So I just threw that out there. I think if I were doing this, I might go with option 2. Option 2 would be to do this. Option 2 would be to multiply through by the LCD, which is cosine squared. So let's multiply everything through by cosine squared x. So let's think about multiplying both sides of the equation by cosine squared. I will get cosine squared x, squared x. Okay, I think I might have got booted out there, so I guess I'll just continue from here. Option 2 would be to multiply through by cosine squared x. If I multiply everything through by cosine squared x, I will get cosine squared x subtract sine squared x equals a negative 2 cosine squared x. And all I did there is I multiplied everything through by cosine squared. So 1 times cosine squared is cosine squared. Cosine squared times this, of course, the cosine squares will cancel. You're left with sine squared. And a negative 2 times cosine squared is a negative 2 cosine squared. If I bring the negative 2 over to this side and call it positive, and let's replace my, no, I won't do that yet. Let's leave this as it is. I'll do that shortly. Let's call this sine squared x equals 0. So now I have 3 cosine squared minus sine squared equals 0. We still have 2 trig identities here, or sorry, 2 trig functions, sine and cosine. How can I possibly make this equation only have 1 trig function? Well, if I were to replace cosine squared with 1 minus sine squared, or sine squared with 1 minus cosine squared, doesn't matter which, I will create an equation with only 1 trig function. So let's do the first. Let's replace cosine squared with 1 minus sine squared. Now, I know you're thinking this is probably a little more difficult than the option 1. And the mathematics of creating the equation probably is, but solving it at the end is actually a little easier, I think. So we get 3 subtract 3 sine squared x minus sine squared x equals 0. So that gives me 3 subtract 4 sine squared x equals 0. So that gives me a negative 4 sine squared x equals a negative 3. So sine squared x will equal 3 over 4. So what does sine x equal? Very important. Plus or minus the root of 3 over 4, which would be root 3 over 2. So let's look at our 2 options here. Option 1, we got it down to tan x pretty quickly, really. Tan x equals plus or minus root 3. The other one took a lot more work, and we got it down to sine x equals plus or minus root 3 over 2. The reason why I like option 2 better is because I can easily solve this one, because I know the answer to that pretty much immediately. This one over here, I got to do a bit more thinking with this one. Because when you think about the unit circle, where is tan x equal to plus or minus root 3? That's not as obvious as where sine x equals plus or minus root 3 over 2. Although they're in the exact same locations, right? So we draw our unit circle. And again, sine, both positive and negative, means that we're going to have terminal arms in each of the 4 quadrants, in this case. So we're going to have terminal arms here, and here in all 4 quadrants, because again, the plus or minus, right? Sine x is plus root 3 over 2 in 2 places, and minus root 3 over 2 in 2 places. Now, where is sine root 3 over 2? Sine is going to be root 3 over 2, being the second coordinate, when cosine is a half, which is at 60 degrees, or pi over 3. So when our reference angle is pi over 3, in all 4 cases, we have the correct solution. So if you look at your solution is going to be pi over 3 is one solution, 2 pi over 3 is another solution, 4 pi over 3 is another solution, and finally 5 pi over 3 is the other solution. So the correct answer here is C. And again, if we look at option 1 is fine. Tan x equals plus or minus root 3. But if you think about the unit circle, that's a little more difficult to see. If you recognize it, it's true though, because tan is sine over cosine. So if I took sine divided by cosine, I would get root 3. Root 3 over 2 divided by a half is root 3. Again, either option is fine. If you could recognize directly from here what the solutions are, then by all means you use that method. Or if you want to use this method so that you get in terms of sine, being a little more recognizable on the unit circle to get our 4 answers. But the 4 answers are what you see here in C. Okay, key ideas. Reciprocal, quotient, Pythagorean, and double angle identities can be used to help solve a trigonometric equation algebraically. And remember to check the solutions for an equation. Check that solution, for an equation do not include non-permissible values from the original equation. And you saw that occur in a couple of places. Okay, that ends this lesson.